Hello everyone and welcome to today's session where we discuss about the secant method, a brilliant numerical technique that blends logic and geometry to give us fast and accurate results. In today's video, we will walk through step-by-step solution to the secant method using two different examples in which we go for detailed calculation and visual explanations that makes the concepts crystal clear. So whether you are just a beginner or revising for an exam, this video is your key to mastering this powerful root finding technique. So let's get started. So we have a question number 1 that find the solution of p is equals to cos of p by secant method correct up to 4 decimal places for the initial approximation p naught 0.5 and p1 is equals to pi by 4. First of all, we need to shift this nonlinear equation into f of p is equals to 0 format. And this is a nonlinear equation because a trigonometric function is involved. Secondly, we need to check that this initial guesses is brackets the root or not, because p naught is 0.5 and p1 is pi by 4. So we need to check that either our root is bracketed in these initial guesses or not. So let's start the solution. So we have p is equals to cos of p. So f of p is equals to p minus cos of p, that is equals to 0. After that, we need to put f of p naught into our equation. So it's become p naught minus cos of p naught. So that is equals to f of 0.5, that is equals to 0.5 minus cos of 0.5, and they give us a solution negative 0.37758. So this is a negative value. After that, we need to substitute f of p1. So we have p1 minus cos of p1. So we have f of pi by 4, that is equals to pi by 4 minus cos pi by 4. So we need to simplify it. After simplification, we will get 0.078291. So this is positive value and this is negative value. So we got the opposite signs. So it means that this initial guesses are fine and the root lies in that range. Now let's go for the first iteration. So the customized formula for secant method is P2. In that case, we are choosing n is equals to 1. So P2 is equals to P naught f of P1 minus P1 and f of P naught divided by, we have f of P1 minus f of P naught. So we need to substitute the values. We have the P naught, that is equals to 0.5 and f of P1 is 0.078291 minus P1 is pi by 4 and we have f of P naught is negative 0.37758. So we need to simplify it, and in denominator we have f of p1 0.078291 and minus 0.37758. So we need to simplify it. After simplification, we get the value 0.73638843. So that is the value of p naught, and we need to substitute in the function in order to find out the value of f of p2. So f of p2 is equals to, we have the function p2 minus cos of p2. So that is equals to 0.73638843 minus cos of 0.7363843. So you need to simplify it. After simplification, you will get negative of 4.519622 into 10 raised to the power minus 3. After that, we need to go for second iteration. So for second iteration, the customized formula is, in that case, we need to substitute n is equals to 2 in our general formula. So the customized formula will be P3, that is equals to P1 f of P2 minus P2 and f of P1. And in the denominator, we have f of P2 minus f of P1. So we need to substitute the values. So the value of P1, we need to extract it from here. This is the value. So we have pi by 4, and f of P2 is, we have negative 4.519622 into 10 raised to the power minus 3, minus P2, we have the above value 0.7363843 divided by, we have negative 4.519622 into 10 raised to the power minus 3 minus f of P1. So we have f of P1, this is the value, that is 0.078291. So you need to substitute here 0.078291. We need to just simplify it, and after simplification we will get the value 0.739062. This is the value of P3. So we need to substitute in our function. F of P3 is equals to P3 minus cos of P3, that is equals to 0.739062 minus cos of 0.739062. So after simplification, you will get negative of 3.871582 into 10 raised to the power minus 5. Okay, so we need to keep in our mind that we need to go for 4 decimal places. This is our tolerance, defined tolerance. So for P2 we have 0.7363, and for P3 we have 0.7390. So we got the accuracy to 2 decimal places. So let's go for the third iteration. In that case, we need to substitute n is equals to 3 in our generic formula. So the customized formula will become P4, P3, f of P2 minus P2, f of P3 divided by f of P3 minus f of P2. We need to just substitute the values. So P3 is 0.739062. F of P2 is, previously, this is the value of f of P2. So we need to substitute it here. So it is minus 4.519622 into 10 raised to the power minus 3, minus, we have P2. The value of P2 is 0.736383, and f of P3 is minus 3. We don't have a space, so I'm just shifting a little bit lower side, 3.871582 into 10 raised to the power minus 5. and divided by, we have f of p3. So that is negative of 3.871582 into 10 raised to the power minus 5, and minus we have negative 4.519622 into 10 raised to the power minus 3. So you need to simplify it. So after simplification, we will get 0.73908. 5. So this is the value of P4. So we need to check either we achieve the accuracy to 4 decimal places or not. So the value of P3 to 4 decimal places is 0.7390, and P4 we have 0.7390. It means that we achieved the accuracy. So hence the correct route up to 4 decimal places is P is equals to 0.7390. Let's proceed to the second question. Okay, so we have a question number 2, that find the real root of an equation x cubed minus x minus 1 that is equals to 0. So the given equation is a nonlinear equation by secant method, correct up to 3 decimal places. Okay, in this question, we are given with a nonlinear equation and a tolerance, but we are not given with the interval. So first of all, we need to find out the interval with the help of an hit and trial method. So we have the function f of x is equals to x cubed minus x minus 1 that is equals to 0. And I'm going to just start putting my values initially for x is equals to 0. So when I put 0, we will get negative 1. So that is a less than 0 value. Okay, let's check for x is equals to 1. So when I substitute 1, so it becomes cancel out, and we will get again negative 1 that is also less than 0. So 0 and 1 should not be the interval because both giving us a same sign. Let's go for 2. So when we substitute x is equals to 2, so it's become 8 minus 2 minus 1, and we will get positive 5 value. Okay, so we have two options, that either we choose an interval 0 to 2 because 0 gives us a negative sign, or 2 gives us a positive sign, so this is a fine interval. Or the second option, that we choose 1 to 2 interval, that is negative and that is positive. Now, this is the smaller interval, but I just wanted to reduce the size of this interval so that the number of iteration will also be reduced. So for that case, I am just checking the middle values from 1 to 2. So I am targeting to 1.5. So after putting 1.5, we will get 0.875 that is greater than 0. Okay, let's go for 1.4 because I'm going to choose 2 points. So it should be 1.4 raised to cube minus 1.4 minus 1. So that is equals to 0.343. So that is also greater than 0. Let's go for 1.3. So f of 1.3, 1.3 raised to cube minus 1.3 minus 1. So the answer should be negative 0.10. Okay, so I am choosing 1.3 to 1.4 interval, and at 1.3 we get negative 0.103, and f of 1.4 we will get positive value 0.343. Okay, let's go for first iteration in order to achieve the accuracy till 4 decimal places. So in that case, I am substituting n is equals to 1. So the customized formula would be x2 that is equals to x naught f of x1 minus x1 f of x naught over f of x1 minus f of x naught. So we have x naught, this is our x naught, and this is our x1. So 1.3 and f of x1 is 0.343 minus 1.4 and negative 0.103 divided by we have 0.343 minus and we have minus 0.103. We need to simplify it, and after simplification we will get the value 1.32304. We need to evaluate the function value also. F of x2 that is equals to x square cube minus x2 minus 1. So we have 1.32304 raised to cube minus 1.32304 and negative 1, and after simplification we will get negative 0.007136, that is less than 0. After that we need to go for the second iteration. Here we have n is equals to 2 and the customized formula is x3 that is equals to x1 f of x2 minus x2 and f of x1 divided by f of x2 minus f of x1. So we need to substitute the value. The x1 is equals to 1.4. We have negative 0.007136 minus x2 we have 1.32304 and f of x1 is 0.343. In the denominator part, we have negative 0.007136 and minus 0.343. After simplification, we will get negative 0.000481. No, sorry. It should be 1.324605. Okay, let's see till which decimal place we will get the accuracy. Okay, so that is the value of x3. Let's check the tolerance. So we have the value of x3, x2 is 1.3230. So here we have 1.324. So we achieved the accuracy to 2 decimal places. So let's move to the third iteration. In that case, we need to substitute n is equals to 3 and the customized formula is x4 x2 f of x3 minus x3 f of x2 divided by f of x3 minus f of x2. We need to substitute the values. So we have 1.32304 f of x3. Okay, we need to find the function value also. So here we have f of x3 is equals to negative 0.3 times 0 481, that is less than 0. So we need to substitute here. 481 minus the value of x3 should be 1.324605, and f of x2 is negative 0.007136, divided by, we have negative 0.000481 minus, and f of x2 is negative 0.007136. After simplification, we will get 1.324717. Okay, so if we check, the value of x3 till 3 decimal places is 1.324, and the value of x4 is 1.324. So we achieved the accuracy after third iteration. So we can simply say that hence the correct root up to 3 decimal places is x is equals to 1.324. And there you have it, a complete step-by-step solution using the secant method from the initial guesses to the final root. So we have seen that how this method smartly avoids derivative and still gives an accurate result. So if you found this video helpful, make sure to like, subscribe and hit the bell icon so you never miss a lesson from the numerical analysis techniques. And let me know in the comment if you have any questions or queries. So thank you so much for tuning in. I'll see you soon in the next video. Stay blessed.